All right, y'all, back with some more linear algebra. We'll go ahead and continue where we left off from with the proof of the spectral theorem. So we left off with the derivation or simplification of s into this value. And now we're going to simplify this dot product. Even though this line from dot product principles. So the thing is, they say using symmetry. Well, maybe we should look back into the dot product rules. So this was the rule here that they used in that line where it was let's see. So the rule is this. I need to adjust this a bit. It's x dot x plus z equals x dot x plus x dot z. So we can say that this is a minus ai squared x plus b squared ix, and all of that is dot product x. So that's going to equal a minus ai squared x dot x plus b squared ix dot x. So using that principle, we have that. So let's go back to the spectral page and see if this matches. It looks like they removed the identity matrix. So basically, this would be a minus ai squared squared plus b squared I squared over it is magnitude squared plus b squared I magnitude of x squared. Now, the identity matrix gives you the same thing, so it seems like they just allow that to give you the same thing. But I noticed they have the magnitude of this squared as well. Okay, so we have a squared x that that x is going to be a squared x1 x2 that x1 x2. So that equals a squared x1 squared plus x2 squared. Unless, that's right, I'm scaling the whole point. So what is this? A squared x1, a squared x2, that x1, x2. So that's going to be a squared x1 squared plus a squared x2 squared. So that's the same thing as a x x dot a x. So let me make sure about this part. But it seems like it'll equal that. The limit will be again a x1 x2 dot a x1, x2. So that equals ax1, ax2 dot ax1, ax2. So that equals a squared x1 squared plus a squared x2 squared. All right. I think that does the understanding of why that is or you can do this when you see that. You can say, instead of A will be this entire thing, but everything else is the same. So that ends up being A minus A I X dot A minus A I X plus B squared magnitude of X squared from the double X. So basically, this is this. And I feel like adding another step here will make this more clear. So I'll move this there, I'll move this here. So this equals A X dot A X. So this more clearly shows the connection, right? So now we know from this that when we have the same thing dot product with itself is the magnitude of that thing squared. So this is the same thing dot product by itself. So it's the magnitude of A minus A I X squared plus B squared X squared. All right. And it says now the only way to sum the two non-negative numbers can be the only way the sum of the two non-negative numbers can be zero is for both of them to be zero. That is, since x equals not zero, the magnitude of x squared equals not zero. And we infer that b equals zero. So x equals not zero. Therefore, the magnitude of x squared equals not zero. So b equals zero, which was the part that made the number imaginary. And a minus ai x equals zero. So that's what makes both of those zeros. And that's how we know that the characteristic equation comes from this. Because a number becomes real for both of those to equal 0. We know x is not 0. So those together must be 0. And x is in the null space of a minus xi, which is why the determinant has to be singular to give us the real value x. Now we proceed to prove the second part of the theorem. Oh my gosh, that was just the first part. That lambda 1, all right? All right, so we got to the first part of that. Out in here, we got through the first part of the Spectra theorem, which is understanding that in order for this to equal 0, b equals 0 means it's real, and a minus ai x equals 0. So we shall come back later and now continue from there, and we'll get the second part of the spectral theorem, and then we'll work an example. So I'll see y'all then. Like, share, subscribe. Be back later.